Okay, so today you're going to learn a skill called implicit differentiation. So what we've done in the past is we've always done explicit differentiation. And the reason why implicit differentiation is helpful is because, for example, is a circle a function? No. It's graphable, exactly, okay? And so we can find the derivative of a circle without having to solve for y. I'm going to show you that today. It's kind of neat. These are examples of explicit equations. Y equals 2x plus 1. Y equals sine of 2 theta. Y equals 4x squared plus the natural log of x. Those are all examples of explicit equations. Here's some examples of implicit equations. 2x plus 3y equals 6. X squared plus y squared equals 100. Yep. X squared over y plus 1 is equal to y to the third minus x. Yeah, that's a good question. What do some of these things look like? Many of these things that are implicit are not functions. The whole idea is that if you have a function, you put in something, you get one thing out. But we know that for circles, for every x value, how many y values are there? There's 2, and that's why they are not implicit. Can you tell me as you look at these equations, what is really the thing that tells you the difference between explicit and implicit? Y equals. And when we take the derivative, often we're misled about what the process actually is. Okay? This is what we use often, f prime of x. So we're going to just talk about terminology, kind of wrap your brain around today. And so the challenging thing, you're all going to be able to find derivatives implicitly today, okay? You're not going to have any problem with that. But the question is, can you understand conceptually what's going on here? That's a different scenario altogether. So f prime of x is generally when we have an explicit equation like f of x equals something, okay? And we then find the derivative. So that's the rate of change of the function with respect to x. And this, if you see d over dx, it's in these type of situations where we like to use different terminology. Namely, d over dx means rate of change with respect to x. Yeah, basically. If we read this, this is the rate So that's different terminology that's used. Maybe this example could kind of show you exactly what we're talking about. It says find the derivative of the circle using implicit differentiation. And so all we're going to do is we're going to operate on each one of these pieces. So I'm going to write this as d over dx x squared plus d over dx y squared equals d over dx 36. Right. So here's what you have to think of when you're doing this type of problem, okay? So here's the important part, okay? What is the derivative of x squared? 2x. What variable were you taking the derivative with respect to? X. So therefore, you just have 2x. With what respect am I taking the derivative of y squared? That's not the same as y squared, is it? So notice that before, anytime we took a derivative, we always listed as f prime or y prime, right? You know that when you take the derivative of this, you're going to have a y prime pop up somewhere. And it pops up right here, okay? And here's how we write it. When you see that you're taking the derivative with respect to a variable, and you're taking, and the variable you're using is different, here's what you have to do. What would you suggest is the derivative of y squared? 2y, but we attach a y prime. y prime. The derivative, so d over dx of y squared is equal to 2y y prime. Okay? Nope. And that's what I'm going to show you in a second. So I'm going to show you this, and then I'm going to back it up, and you guys will see it. Okay? You'll see it. Okay? Equals, what's the derivative of 36? 0, and it doesn't matter what respect the variable is to, because 0 times anything will be 0. Now, we'll deal with that in a second, but I know that that's difficult for some people to see, so I'm going to bring you back. Nothing to write down, but this should now tie your learning together. If I have this equation, y equals x plus 4. I got to change this. Y equals 3x plus 4. Okay? Everybody okay with that? Okay? And you want to find the derivative. Okay? Watch what you do. What is the derivative of y? 1, and you always attach a y prime. We don't write the 1, but it's there. The derivative of y was 1, and you attach a y prime. What's the derivative of 3x? 3, and the derivative of 4 is... So, I'll write the same equation. Okay, watch this. I'll subtract the 3x over. Negative 3x plus y equals 4. Everybody okay with that? I'm going to multiply it through by 2. Negative 6x plus 2y equals 8. Still same equation, right? So when I take the derivative of that, I should still get y prime is equal to 3, correct? So we'll do it in an implicit way. Before we did explicit, now we'll do implicit. What's the derivative of negative 6x? Negative 6 plus derivative of 2y with respect to x is 2, and I attach a y prime. You know that that's got to pop up somewhere. Equals 0. Add your 6 to y prime is equal to 6. Divide by 2, and you get y prime is equal to 3. So you still come up with the same thing. Okay? Well, you have to account for the 2. It's twice. You would take the derivative just like normal. Derivative of 2y is going to be 2, but you have to attach that y prime. Just like before, when you had y equals 3x plus 4, and you took the derivative of 3x plus 4 was 3. The derivative of y is 1, and you attach a y prime. Okay? Now, that's why you can understand algebraically. In terms of calculus, we can maybe look at another example why that works out tomorrow. So right now you have to trust the process of why that is the case. But this is now easy to work through. What do you think we want to solve for to find the derivative? We want to solve for y prime. So how do we do that? Yep. So you get 2y is equal to negative 2x divided by 2. Whoop. So y prime. I'm sorry. 2y, y prime is equal to negative 2x. Divide by 2y. And we get y prime is negative x over y. Now, I don't know what you're asking. I'm trying to think. No, y prime is 2y y prime. Here's the deal. You can do this. Right now we're taking the derivative with respect to x, right? If you would like to take the derivative with respect to y, go ahead. The derivative with respect to y is going to be 2y and 2x x prime. It depends on the variable you're taking the derivative with respect to. Okay. We will always take with respect to x. Okay. We won't do that differently. Okay. We'll summarize this in a second. I want you to flip over to the next page so you can see another example, and then you'll all get it. We are. But first, we're gonna do this part. I'm thinking Tuesday or Wednesday next week. So, use implicit differentiation to find derivatives of the following equations, okay? I want to find the derivative of 3x squared minus 4y equals x, okay? I'm taking the derivative with respect to x. What is the derivative of 3x squared? 6x. Minus, what's the derivative of 4y? 4, and then I attach a y prime, equals 4. Four y prime, very good. Yep. What's that? Oh, 8 y prime. Yep. Okay, so then I subtract my 6x. I get negative 4y prime is equal to 4 minus 6x. Divide both sides by negative 4. Y prime is equal to, I guess you could write as 3 over 2x minus 1. So if I divide negative 6 by negative 4, I get the 3 halves. 4 divided by negative 4 is negative 1. So that's one of the more basic examples. Let's try one that's slightly more difficult. Let's look at letter B. Can anybody see why this is going to be a little bit more difficult? Yeah, there's more than one y, and the y is raised to a different power. So let's tread slowly here. What's the derivative of y to the third? 3y squared y prime. Every time you take a derivative with a y, you have to attach a y prime. Sorry. Minus 5 plus 2y prime equals 3. So, We'll fill out the summary in a second, but the first step is to always take the derivative with respect to x. The second step is to always remember to attach a y prime when you take the derivative of a variable that has y. The third step is this. Gather all the y primes on one side and everything that doesn't have a y prime put on the other side. So I have this 3y squared y prime. I have a plus 2y prime. I'm going to bring the 5 over on the other side, and so I get equals to 8. Everybody okay with that? What am I trying to solve for? Y prime. So the fourth step here is to do what? To pull out a y prime. If I factor out a y prime, I get 3y squared plus 2. We did some things last year in college algebra to prepare you for this step. Yep. Always thinking scope and sequence. And now I divide by the 3y squared plus 2. So y prime is equal to 8 over 3y squared plus 2. So, whoops, sorry. And so what you see here is that, there's some just nice little algebraic techniques to work around some of the issues that come up in calculus. So let's write down the summary again, and then we can do another problem. We'll finish off these couple. So the first thing is derivative with respect to x. And we choose x because when you write, say, a tangent line at the end, you're always going to say y equals something times. We always express it as y is the dependent variable. Okay. Second step is attach y prime Make sure you attach y prime to all your y variables when you take that derivative. The third step, gather all y primes on one side. And the fourth step, what do we do that Larry said? Factor out y prime and divide. And you're done. Go break a leg! Let's cheer for them. Yay! What? Yeah, I'll put it at the end. I don't have it right now. I have to look it up. Yes. So, let's pick up with example C and D, and then I'm going to do one more example that involves another circle, and you guys will get it. It looks great, okay? So, I take the derivative with respect to x. What's the derivative of x? 1. What's the derivative of 2y squared? 4y prime. Yep. So again, you just got to make sure you attach all your y primes. Now what's the next step? Get all the y primes on one side. So now I know Sydney meant this, but it's very important when she said, if it just has a y, we don't care. It has to have a y prime. If it has a y, it's going to have a y prime. But that's the idea, okay? It's got to have a y prime. So we've got 4y prime minus 16 y to the third y prime equals 9x squared minus 1. what to do. Y prime or y 16 by the third is 9x squared minus 1. You could factor it, see if something would cancel, but that's just not going to be the case. 9x squared minus 1 over 4y minus 16 by the third. Yep. Yep. So if it differs by a factor of -1 on the top and the bottom, -1 over -1 is 1, so you would have the same equivalent expression. So that's very possible in these situations that people would move them to the right side instead of the left side. So is that what you did? Yep, that's fine. Well, Solveig caught it before she left. What do you think? 3xy. Product rule. Yep. So, before you get all angry, let's just do the rest of the problem because that part's easy. What's the derivative of 5y squared? And y prime? What's the derivative of 9x? And again, every time I say what's the derivative, I should always say what's the derivative with respect to x. I mean, that's the point of this lesson is that, you know, whatever variable you're taking the derivative with respect to, you don't have to attach something. So now we got 3xy. So I'm going to call this my first function, and I'm going to call this my second function. Okay? So the product rule, what's the derivative of 3x? 3 times y left alone plus 3x times 1y prime. You see how this is the product rule with that? Okay, so product rule says derivative of this, just 3, times y left alone, plus this left alone, 3x, times the derivative of y. And you all know that the derivative of y is y prime. And as soon as you say to yourself, why isn't the derivative of a y just 1? Well, remember, every time you do a problem like this, you would never write 1 equals 2. You would never do that. You would write y prime equals 2. You've been doing it all along, you just didn't know it. And I did give you a little hint a few weeks ago that that's actually what you were doing, if you remember. We did go over, Casey thinks I'm lying. Okay. Don't you shake your head at me. What? Pause. Okay, what do I do next? 3xy prime minus 10y y prime equals -3y minus 9. Now what? Factor out the y prime. 3x minus 10y equals -3y minus 9. And so we end up with y prime is equal to -3y minus 9 over 3x minus 10y. Everybody see that derivative? Where? Right here? Yes. So that is one example where you could have a y with not a y prime, is say in the product rule. It does get left alone. So, yep. So I said before that if you have a y, you'll always have a y prime attached. That's technically not true. You see in the product rule, here's the situation pops up. Okay, let's top it off. This is something you've always wanted to do. Just write this down. X squared plus y squared equals 25. Find an equation for a line tangent at -4, +3. This is great. Because the circle is not a function, right? Yet we're still gonna find a line tangent. And so you'll see how to use it. Okay? It's really cool. It's really cool. In order to find a line tangent, what two pieces of information do I have to have? Point on line and the slope. Do we know the point on the line? How do I find the slope? Derivative. What's the derivative of x squared with respect to x? Y squared equals 0. Solve for y prime. 2y, y prime is equal to -2x. Just like we did on the front side, we come up with the same thing. Y prime is equal to -x over y. So, if I want to come up with the slope, what do you think you plug in? You plug in x and y. So, -4 over 3, so +4/3 is your slope. Can you now write the equation for the line? Piece of cake, upside down. Go ahead and do it. I'll pause and put the assignment up there. I know that I know that you probably got a lot of work to do already. We do have one more assignment after this, and the next assignment that we have is very, very, very simple. Okay. So again, two reasons why you got to hurry up. Number one is that you want to save time at the end of the semester, final exam, right? So that means we got to be ahead of where we were last year. Second of all, we need to get this tested before Thanksgiving, so or just not have a final.